So let's get started with the first presentation. Sharid Amiri is with Caltrans, and Sharid, the floor is all yours.
Thank you, Gerald. So I'm going to talk about the use of the CPT or cone penetration test in a design-build project environment. And that's a case study here in California, Southern California. It's a mega project. It's been going on for years and due to be completed by 2024. So it has to do with one of the busiest, arguably one of the busiest highways in the country as far as the traffic demand is concerned, and that has to do with the Interstate 405 design build projects here in Orange County, California. For those of you who've traveled to Southern California, you will see that this road is super busy and always has basically a huge traffic demand throughout the day and throughout the week. This specific project, it's a $2 billion project. It has to do with the 16 miles of road widening. And basically, what happened in this project was that the focus on my engagement was the bridge structures. Of course, it has lots of retaining systems, more than 100 of them, and widening lanes, and also either replacing or widening or brand new bridges for this project. As far as design build is concerned, as I'm sure those of you who've been involved with design build projects know very well that design build are in general very aggressive. Project deliveries time is, like anything else, is very important, time saving, and more importantly, if you can come up with some innovative solutions to deliver your projects, that's one of the hallmark of design build projects. So this was no exception. As part of the design build project, the requirement here in California is and other design builds for that matter, is to prepare a what's called TP or technical provisions for this, which is a document that basically sets the standard and expectations from the design and construction team on how to deliver the project from a technical point of view. And in this case, what happened was Caltrans, where I'm employed at, we collaborated with the local transportation authority who mainly funded the project, OCTA, Orange County Transportation Authority. And in this collaboration, we developed technical provisions for the contract and requiring the use of CPT cone penetration test as part of the site characterization program. Why is this important? Because if you don't basically prepare a well-developed TP, which supersedes, by the way, all the other technical elements in a project, you run into the risk of either not being innovative enough or taking too much risk. So it's a balance act between using of technologies that perhaps could be used to deliver an efficient and safe project, but at the same time you want to balance your risk with that. So design build projects, in my personal opinion, provides that opportunity for you to do that rather than a design build projects. Here I'm going to be talking quickly about, and I'll talk later during the slides, about bridge foundation design. So as you know, the bridge foundations for basically construction and design for the bridges, conventional bridges for that matter, here in Southern California, are typically designed using borings, and if exploratory borings, as part of the site investigation and site characterization. And this project was the first use of the CPT technology in the direct design of bridge foundation. By that I mean, you basically got the CPT data and you design your foundations. You didn't have to worry about correlations or using changing CPT data to SPTs and then designing your foundation. So this was the first use of a CPT technology in direct design of bridge foundations for a project of this scale in California. Now, if you're in California, you're, for that matter, in seismic states in the United States, you have to basically deal with in your projects with geoseismic issues, the impact of earthquake and its geoseismic aspects of the earthquake on the design of your foundation and your bridges and your basically geotechnical assets. This project is in a seismic zone, and it was subject to liquefaction, which is an earthquake-induced phenomena that leads the subsurface soils to lose its strength, its shear strength during a design earthquake event. So as I'm sure you can understand, the gravity of this with respect to the bridge foundation design and also the objective of this investigation and CPT was to basically provide a continuous profile, right? And that's what CPT does. Unlike your borings that you don't have a continuous profiling of your subsurface characterization, CPT has this excellent capability to do exactly that, a continuous profile, and basically accurate depiction of your subsurface soils. And why is this important? Because in the context of geoseismic, you want to capture those liquefiable soils, and if you don't capture them, obviously you're introducing risk and lack of a good performance for your bridge foundations in the long term. So that's an obvious point of using CPT, which we did in this project. And so, as I mentioned, the geoseismic, we also want to say that, and I mentioned that earlier, is that the objectives of this design objectives of the CPT was achieved by making the use of CPT a requirement for this project, right? So if you don't make it a requirement, the contractor does not have any obligation to do it, right? So we mandated that in the TP, in the design build, and you don't have that luxury of doing that in the design bid build, because the design bid build, they just follow your guidelines and they say, well, we do what we think is right. We follow your guidelines, and nowhere in the guidelines we say you have to use this or you have to do that. But in a design build platform, you have the capability to do that, and we took advantage of it. Of course, when you do that, and speaking of design objectives, you have to have, as I'm sure you can understand and appreciate, a keen understanding of the local geology and conditions at your site before you apply this mandate in your TP. So as I mentioned earlier, the objective was to investigate and characterize the site, each bridge, by a combination of CPT and borings, nevertheless, but the CPT basically dominated the profiling, and also a direct design of bridge foundation. That was not mandated in the TP. However, when we mandated this use of CPT, it was a natural conclusion that why not use this data to directly design the foundations? And that's exactly what we did. What the consultants did. I was in oversight capacity. I just want to state that. So now, for those of you who are not familiar with CPT, it's basically a cone that gets penetrated into the ground by a cone truck that pushes the cone, and it's standardized under the STMD 5778. You can always refer to that for more information. It gives you a slip friction, pore pressure, and then measure cone resistance, QC. FS is your slip friction, and using these two parameters, you can basically design your foundation accordingly. It has a constant push rate of about 20 millimeter per second, and it reads every 1 to 2 seconds. And the rod diameter is shown there as far as 36 millimeter in 1 meter length. These are all in metric, of course. And the beauty of CPT, as I mentioned, is that it's a continuous profiling. It's quick, and I'll talk about that later and how much that helped us in a variety of ways, not only from a cost-saving point of view, which is obviously very, very important, and that's the topic of our discussion here, but also other elements, which I'll talk about it in a few minutes. So the CPT calibration. So in every job, you need to have your CPT being calibrated, right? So this was no exception. We wanted to make sure that we do that. But also by that, I mean also we required in the technical provision that for each bridge structures, you have at least one side-by-side CPT next to the board. Reason we did that is because we want to get the data on CPT next to the boring to see how they calibrate against each other for a site-specific aspects of the board. Of course, there's a lot of data, right, for CPT and boring comparison, but there's none for this local geology here in Orange County, and this goes a long way in your LRFT design of foundations later on and building the database to give you even more confidence on how the CPT and borings correlate at the specific location, rather than just use a generic data that is available in the literature. And we did that. That was a mandate in the TP as well. We developed that collaboration with the Orange County Transportation Authority. So not only we use that for investigation, but we also use that for investigating the liquefaction potential using both SPT and CPT. So this was another calibration that basically calibrate the performance of CPT and its power in evaluating liquefaction directly, and compare that to the SPT evaluation of liquefaction and draw a comparison, which is, in my opinion, is very valuable and priceless in the areas when you do seismic design of bridges. So as I mentioned, I did talk about use of CPT primarily for design of foundations, but the focus even was more at the pier, at the bend supports rather than the abutments. So the reason for that was because of many reasons. This is a highly congested road. Traffic is on it all the time. So because of construction, one of the reasons was construction reasons, right? You want to have lower footprint, lower impact on the traffic, and a lot of other elements that got into it that we try to, we focus on beds, primarily using the CPT, but in some areas we do the abutments as well. But primarily abutments we're using borings. So the other element of using CPT here, core penetration test, was using GINT data. This project started back in 2017, but the TP was developed back in 2015. So the site investigation was basically compiled both in PDF and GINT. And this is important also because the CPT data now is in GINT, which is interoperable data that you could use for a variety of things. And later on in the long term, it even could be used using artificial intelligence, but that's a different topic. But that's what's the potential for this is as well. And it's also very much in line with activities of digs, which is happening nationwide. So, and for those of you who may not know what GINT is a data management software that allows data accessibility and interoperability. So that was also another facet of this project. The site characterization. So as you can see on this profile, this is a one given bridge among many bridges that was designed for and built in this project. The blue color, if in case you wonder what those are the liquefiable layers at the site. So as you can see, you can have a clear picture of where the liquefiable layers are. Why is this important? Because it was part of the mandate in the TP technical provision for this project was that you cannot have batter piles in soils that are settling due to seismic or static. So basically, we don't allow down drag of soil on batter piles. So batter piles were not used at the abutments. And if you can see this liquefiable layer, not just only that for that, but for many other reasons, right? You want to design your foundations based on the impact of liquefaction. You have to capture that under extreme events, which was the case here. And so I want to talk about quickly a little bit on site characterization rather than the site investigation. That's another, element here, right? Like any other projects, you have to come up with your NK factor, and I don't want to get into the detail of that. But basically, the NK factor for CPT was evaluated, calibrating the values of the CPT and shear strength and cohesion. That was happened by performing triaxial tests for cohesive soils, which was required. And then due to the abundance of the CPT data, as you can imagine on this project in the hundreds, we could get a nice picture of where the NK factors are and apply that to design our foundations. And the other thing was the VS30, which is the shear wave velocity in the upper 30 meters. And I'm sure for those of you who do get involved with the seismic design, you're quite familiar with that. And we use that directly by using seismic cone penetration test, seismic CPT or SCPT, for developing ARS, which is your acceleration response spectrum that you need to design of your bridges. Back to bridge foundation design, I like to show this photo of the project here. We did use, as you can see, the steel-driven open-ended pipe piles. Some of these were converted to KISS piles because of the structural aspects of the connections to the pile to the cap and the columns. And as I'm sure it could be appreciated, that the use of these pipe piles and steel open-driven pipe piles, it's very important, especially when you deal with liquefiable and lateral spread, which in some of the cases was that. And even without that, these are robust foundation systems for lateral loading and seismic. And you can drive them very efficiently in the geology that we had here, which is basically alluvium sites. And there was no bedrock or rock or boulder or anything like that. And these pipes, these open-ended steel pipe piles were 24-inch, and the method that we used for design of that was the LCPC method, which is the French method. In other words, used to evaluate the pile axial capacity, and the pile load capacity was also verified, which was required in this job for these type of foundations for each bridge structure doing PDA test. Now, I want to emphasize that even though we use LCPC method, it's very important to appreciate that given the abundance of data that we have here and the calibration that we did side by side and the lab testing and other elements in this project, one can easily use this data to come up with a site-specific, perhaps, or even help that data to come up with a site-specific design method using CPT for these type of foundations. And we also had the depth of the plug in, the soil at the bottom of the foundations, and each measured during construction as well. So we have that data as well. So the CPT was also instrumental, as I mentioned earlier, in detecting potentially liquefiable layers due to design earthquake event, right? And again, it was used for lateral design of bridge piles due to earthquake events. And it was also used for seismically induced downdrag to liquefaction. So you can see the different facets of CPT for this job, not on site characterization, but also on geoseismic, on shear wave velocity, on characteristics, etc. The direct. Yeah, I mentioned that already. Okay, so data and its impact on design methodology. So given the extensive data, as I mentioned, gathered on this project, on both CPT terms, in terms of basically characterization and design of these piles, future research can be done to better understand the behavior of open-ended piles. There's a lot of data here that we can be used. As I mentioned also is that design methodologies for LRMC design can be also improved with emphasis in the site-specific design issue. We have that as well, the borings and the CPT and the calibration. And last but not least, the interoperability of the data for this project using GIDS can be also a valuable source for developing algorithm for prediction of the site characterization and pile design capacities. By algorithm, I'm talking about maybe machine learning or other AI elements. So advantage of CPT to boring this project, it provided continuity, right? It is a powerful technology in detecting problematic soils, be it liquefiable or subsoils. It's much faster than conducting borings, almost 4-to-1 it was measured on this project. Powerful technology in evaluating soft cohesive soil, soft clay, which were present at this site in some of the bridges. And also other important advantages in terms of safety, environmental and safety and environmental stewardship. And I guess that's the continuation of that. It was kind of, some of them are actually a repeat of that. I don't know how that happened, but it happened. Okay. Apologies for that slide. It's a repeat. Okay, so cost saving. For all the reasons that I mentioned, how fast it is, how efficient the CPT is, and how quick you can get the data and not convert anything, it has a tremendous cost saving. Not only that, You don't have to worry about lab testing. That's a cost saving. You don't have to transport the sample to a lab, maybe sometimes miles away. That's a cost saving. So these are all, and also the number of crew is less than for a CPT typically than it is for investigations, and also the footprint. So there's a lot of cost savings for that. Time saving obviously is a lot faster than a boring. So there's tremendous time saving of using CPT for this kind of site and geology. 4-to-1 almost, as far as time is concerned. So you can do basically 4 times the same data that you can get it with CPT 4 times faster. Safety. Now, why this is important for every project, and of course, paramount projects here in Southern California, as I'm sure you can appreciate and understand, but even more so for this project, because 405 is just a huge traffic load. And also a lot of that investigation was done at night. Reason for that was because we don't want to go out there and do the investigation during the day because it requires lane closure, and lane closure was just a no-no unless it was mandated for extreme conditions that required that. The preferable way and the way it was contractually agreed was that they want to do it at night. And at night it's a different environment, and CPT was much more, in my opinion, safe than doing borings next to the traffic at night. Environmental stewardship. Well, you don't use you don't travel miles to take these samples out. You finish your job faster. Those are, and as far as that's concerned, your emission, right? When you drive these trucks, your cars, you're sampling. You take these samples for labs, from borings. That takes a lot of fuel and emission and everything else. So that to me, that's CPT, at least in that aspects of it. It's much cleaner and more environmentally friendly than using borings or other means. So in summary, this technology was used for subsurface characterization, but it is not used. But it was not typically this technology is not used for direct design of bridge foundation statewide in California. What basically made this project unique was that it was a successful implementation of this technology on a mega project in Southern California. And it can lay the groundwork for the use of direct foundation design using CPT for other projects coming up. It had a tremendous cost saving due to the use of CPT instead of borings only, and which amounted to an estimated of $7 million for this project. So it was, in my opinion, a tremendous saving for this project. So with that, I think I'm done with my presentation, except one last slide, I guess, is acknowledgement. I would really want to appreciate the efforts and the work that was done on this project as with regards to Caltrans District 12 Orange County, where I provide my technical support to. Caltrans Office of Structural Construction, which were instrumental in during the construction phase of the project. And last but not least, Fuber Consultants, who were the prime designer for this project. Thank you very much.
Thanks, Sharid. And obviously, as a committed cone head, it's nice to hear a project where CPT is being applied. A couple of questions though that came up. You said at the very beginning of your presentation that this was the first time that CPT was used for a direct design. If you did your design directly based on the CPT data instead of all kinds of other lab data and boring data. Since this was a success, is there a tendency now to do this more often, or will this remain a one-off?
That's an excellent question, and that's a question that was asked internally. As you can imagine, Caltrans is a huge DOT, and we're just part of that huge family of folks. So this question came up. It went to the attention. Actually, this project was awarded for innovation solutions to a project by our director and our geotechnical services deputy. So it's in the radar, and they would love to use this for other projects as well. The challenge with that is that you don't come up with mega projects like this as often. This was the biggest projects in the state of California at its time, and probably arguably even now. So we had the luxury of using this tremendous data along a 60-mile corridor to basically build confidence on its use and calibrate the data. But as I mentioned earlier, it's a start, and I think we're doing everything in our power to promote that in other projects throughout the state as well. CPT is used in Caltrans. We have our own CPT for site investigation, but it's not being used for direct design. So that's one thing that we need to basically promote, and I think this project goes a long way to do exactly that.
Okay. Another thing that came up was obviously with CPT, you have your, what you mentioned, continuous profile. So therefore, in a way, you are doing more testing, not just at specific points, but to get a continuous profile. Do you think that because of that, some liquefiable layers were identified that you would have otherwise missed and would have had an impact on the design of the foundation itself?
Yes. So the question is, if you would have not done CPT, is that what you're saying?
Yes.
Yes, absolutely. And that's what I think I alluded to that earlier. That's another great question. And that's exactly what we did. You know, because of the mandate for using batter piles and for not using batter piles in liquefiable soil, we had to make sure that we have a great and robust site characterization to capture those elements. Otherwise, you know, some could have argued we use the borings and we don't capture those layers. There is no liquefaction, and we would have ended up using batter piles. So in that aspect, it helped. Not only that, it reduced the risk of you know, change orders or perhaps even RFIs and claims, because you know, if you could argue that, well, no, we think there is liquefiable, and the contract says, no, I don't think so. My borings doesn't show any of that. CPT went a long way to basically you know, bring that element of I guess better communication with the design build team and a smoother and more efficient delivery, which happened in this case. So it was an excellent tool. I don't know if that answered your question or not, but
yeah, it does. You said that the piles were subjected to pile driving analysis during installation. Was static load testing performed as well to calibrate again the PDA data against the static load test results, or did you purely rely on the PDA data?
Another great question, Gerald. We as much as I would have loved to have a pile load test on this project, the Caltrans requirement is that if you have anything more than certain amount of diameter of the pile and certain amount of load, then you require pile load test. And in this case, the diameter was only 24 inches, which requires only PDA. For us, we could have introduced that into the TP, as I mentioned, just like we introduced CPT. But to do that, it would have required an extra cost to the project, which was hard to argue for, unfortunately, just because they would go back and say, well, your own guidelines doesn't require it. How come you're asking for that? So, you know, because there's a cost element to that, we didn't go that route. But the PDA tests were done at least one and sometimes two for each bridge structures because of the control. I'm sure the control zones, and some of you who've done this are aware of that. And CPT again was an excellent tool to capture the difference between the control zones and establish the number of PDA tests for each bridge, which we did. So there is that as well. So
okay. One final question for now. What were the soils that you were encountering? And presumably you did not have any gravels in there, or did you have some gravelly soils there as well?
No, the gravel was not there for the most part. It was silty sand, sandy silt, clay silt. The geology here, it's a lot of inner layering. So you have like silty sand, then you switch to sand, then clay sand, clay silt. So the CPT is excellent for that, obviously. So that was another element. The inner layering was there, and also at greater depth we had very dense sand. So that's where we basically terminated the tip of the pile, that part, which was at the depth of about, in some areas 80 or 100 feet, or maybe deeper. But that's about it. The length of the piles were pretty much in the area of 80 feet or so, approximately.
Okay. So Sharid, thank you very much.
My pleasure. Thank you.